Last time we were doing our net force diagram, and we had a inclined plane with a box sitting on it. The example that's given in the book in chapter 4 gives a crate of some sort, and they actually put some numbers in for the force of gravity, the normal force, and the friction force. And so I just want to continue with that and solve this through a bit so that we could get a little bit more practice and a little bit more experience in seeing how to calculate the net force on an object. So let's do this. Let's take and make ourselves a little bit of a axes here, and that way we can think of this in terms of a nice coordinate system here. Here's our axes. Okay, so we just put ourselves a little XY axis in here where this will be like my X and this will be like my Y. Now, when we want to find the net force acting on an object, the last video, we said that we can draw these axes for X and Y, and then we can get the perpendicular components of our forces, and then we could sum them up. We could sum the X components up, we could sum the Y components up, and just like we did before with vectors, we could come out with a final net vector, net force vector. So when we do this, the reason we put the coordinate axes like this is because notice then that what we have sitting over here is this force here, normal, is now simply on the y-axis, and we don't have to do anything further with that. The force of friction then is sitting right on our x-axis, so we got that solved. Now the only thing that we have to worry about is the force of gravity, which is straight down. If this is the, let's say this is the earth over here, or a flat floor, or not so flat floor, as the case may be, gravity is going to go straight down. It's not going to go at an angle. So now, in order to solve the net forces on this object here, we need to get the components for gravity along the x direction and along the y direction. And if we do that, let's do it in green. This force right here down is going to be the component of this gravity force along the x-axis. And if this is 35 degrees here, this angle in here is going to be 55, because you could think of this as making a kind of a right triangle. So this is 35 here, this is 55. So this force right here, this force component in the x direction, is going to be the magnitude of the gravity vector, which is 22 newtons times the cosine of 55. So this is going to be 22 newtons times the cosine of 55 degrees. In a similar fashion, the y component to the gravity vector, which is going to be here, is going to be 22 times the sine of 55. And that's going to give us the vector that way. Now we don't have to worry about this anymore. We've got 4 orthogonal or perpendicular vectors, and we want to start calculating the net force. So let's look at the net force. The net force in the x direction. The net force in the x direction is then going to be, well, it's going to be 22 cos 55. That's, and this, let's say this is the plus x direction going to the right. As we always, by convention, we say to the right is going to be plus. So we got the force vector of 22 times the cosine of 55 to the right. To the left of that, we've got 11 newtons. So we said that in yellow, so we're going to have minus the 11 newtons. All right. And this is going to be newtons as well. All right. Now the net force in the y direction is going to be 18 newtons, that's positive, minus the 22 sine 55. Now, you might notice something here, and I'm going to predict in advance that this number right here is probably 18, or very, 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 very close to 18. and we're going to have to do some estimation for sine of 55. And the reason is because it's the forces in the y direction have to balance out. There's a sense of equilibrium. So we'll discuss something called equilibrium now. So equilibrium. What is equilibrium? Equilibrium is a balance. If we have a tug of rope, and here's our rope, and there's, remember when they do tug of war, they put like a little ribbon on it, and you have two guys pulling, you know, one guy on this side, or a team pulling this direction, and they're going to be pulling the rope that way, and you have a team of guys or people on this direction pulling the rope that way. And if they pull with equal forces, so if he's pulling with 10 newtons of force and this guy over here is pulling with 10 newtons of force, what happens to the red ribbon? It stays still because the system is balanced. And balanced, and then we have, in this case, no motion is going to occur because the forces balance each other out, and you're not going to have the rope moving in this direction, in this horizontal direction. Well, look at it over here. The box is sitting on top of a board, and the box is not flying upward into the air, or it's not falling through the board. Therefore, the forces in this direction, whether they're the normal force or the component due to gravity here, they have to balance each other out, and that's what we mean when we talk about equilibrium. So we have a balanced force, so the net force acting in the y direction then has to be 0. I wonder why that happened. Oh, losing power here is what's going on. All right. We'll have to plug in soon. All right, so this has got to be 0. Net force in the y direction. The net force in the x direction, if we do this and we calculate this, we're going to come out with, according to the book anyway, let's see what the book says. 2 newtons. This whole thing is going to come out to be plus 2 newtons, which means that our box that was once sitting over here, we got balanced forces in this direction, so there's no motion in this direction. However, in this direction, we've got a total net force in the x direction, so our net force in the x direction is equal to 2 newtons. And when that happens, when you get a net force acting on an object, the object then has the potential to move, all right, and to have an acceleration. And that is what we're going to be talking about in the next video. We're going to talk about Newton's second law of motion, which has to do with the net force acting on a body. If there is a net force, it can cause an acceleration. And we're going to see that in the next video.